Greetings, welcome to another Insight Project video. So what I thought this was going to be about was showing like, oh, I'm making some progress homebrewing a battery. I put in a strong electrolyte solution, and now we're getting 2 milliamps per square inch of battery. Isn't that neat? But as so often happens, once I start to do something, and once you get your hands dirty, it's not like I don't see anything abnormal. It's like I get to the point where it's like, just show me anything that's still normal. And that's, of course, what happened here. So everything went off, But to kind of do the spoiler alert here, I ran right smack dab. I ran right smack dab into Piezo, however you want to say it, piezoelectricity, which is, when you deform a material, it gives off a voltage. Likewise, if it gets a voltage, it deforms. And I use balsa wood as the spacers. It turns out balsa wood's piezoelectric. Who would have thunk it? So there's that, and then piezoelectricity doesn't behave the way I thought it did. And there's that too. So this is one of those where, you don't need to build a Arduino circuit. You don't need MOSFETs. You don't need solid state relays. You don't need reed switches. If you just have some balsa wood, a voltmeter, and some different metals, then you can see what I'm talking about. So this is one that anyone can repeat. So why don't we take a look now at what I'm talking about, because I found this rather interesting, and you may as well. To get started here, I'm going to start over from scratch. So what I'm going to do is I'm going to cut a virgin piece of zinc, and same with the copper. And then likewise, this balsa wood, it's never been in any sodium hydroxide or baking soda solution. And so there won't have been any electrochemical changes to the plates. They won't have any residual electrolyte on them or anything like that. And then I'm going to sand them down. And you do that because when you're using this as a battery or voltaic pile, you want to increase the surface area as much as you can. So, I sanded it the first time, I'll sand it this time. But we'll go from there. So let me do that. So this may bore people to tears, but I don't care. When I actually figured out what was going on here, it was sort of like, are you kidding me? I can't believe that. But there's, it's like some people, I can't ever see anything abnormal. It's like every time I get my hands dirty, it's like I can't even find anything normal anymore. So that's sort of what's going on here. Now, if we were going back to using this as a battery, you have two plates of different electronegativities. So you stick it in a solution of electrolyte, and there are two redox reactions going on that create a voltage. And, people can sort of be like, well, he's silly doing a battery from, 1800 or something, voltaic pile. If you look up what were the batteries used on the moon mission, they were zinc silver oxide. So, I have the zinc. I don't have silver oxide. I've got a little bit of silver. But those are arguably still the best rechargeable batteries that have been made. I have an idea for even something you could do with electroplating. Something that might be better than silver. All right, let me not get too far off topic. So this was just like, what the heck is going on? When I realized what's going on, as I said, it's like, oh my gosh, are you kidding me? So let me shut up and show you. And this is, I've hesitated to show this because, it's been strange enough. A lot of times, you see something weird and, oh, look at this, everyone. And then 2 days later, you're like, oh my gosh, please, I hope no one saw that. You figure out, oh, it wasn't that at all. But I've done this enough now that I think this is what's going on, and it blows my mind. So the first thing is we have our two plates of different electronegativity. I just have balsa wood lying around, so I use balsa wood as a spacer. And, it's sitting there, okay, that's just like residual. So then I go, well, let me, this thing came off, so let me try and fix it. So I'll just put my thumb here. All right, that's a little different. Now I'll put both fingers across both plates, like that. It's like, oh my gosh, what the heck is that? That one took me a little while to figure out, but it's actually not that complicated once you think about it. I'm I'm a big bag of salt water. There's sometimes people say worse, but I'm the electrolyte. The little rascal is using me as the electrolyte, and so per the electronegativity difference, maybe you would get a volt with, and we're not that far off, but it's getting 7/10 of a volt through my skin because I have a lot of salt water in me, and so there'd be the galvanic corrosion and things like that. But now I'm going to do something different. Now what I'm going to do is, this is just a rubber thing that you use to open difficult lids on a can. So this is all insulated. Okay, so the glass is actually already insulated. So I got the rubber around here, and there's plastic as well. So I should be well insulated both from the plastic and the glass. And now I'm going to press on this. And well, there, it's just sitting there. Now I'm adding pressure. Adding more pressure. Now here's the interesting thing. Let me just add a little pressure so that it's not difficult for me. I'm just adding a little pressure there. And I'm keeping the pressure, and I'm keeping the pressure, and I'm keeping the pressure. So do you start to get why I said, oh, wow. Add a little more pressure. Eventually that balsa wood will be a problem. So now, what is going on? And there's an explanation. So the explanation for this is that apparently wood is somewhat piezoelectric, and that occurred to me, and well, probably, but it's not that crazy. There's a lot of carbon. Certainly there's a lot of research on like carbon nanotubules and how piezoelectric they are. So there's a lot of carbon in there, and wood has piezoelectricity. I've known for some time that your bones are piezoelectric, and when you go walking and stuff, it's generating electricity through piezoelectricity in the bone, and the patterns that you generate help with remodeling of the bone. So if you go to the gym and do the stair stepper for a while, part of the signaling is the piezoelectricity of the bone. So it makes sense to me also. The wood is out in the forest, and it's had 3 windy days in a row. Okay, we got to remodel a little here. And so wood is piezoelectric, but I didn't think that's how piezoelectricity worked. those rascals. So just to back up for a moment there, what is piezo or piezoelectricity? I'm not sure how you pronounce it. It's the property of a material when put under mechanical stress to generate a voltage. And so you have piezoelectricity, you have pyroelectricity, where under heat it puts out a voltage, and you have ferroelectricity. We'll talk a little bit more about the last one in a minute. But this is piezoelectricity, and that's not how I thought it worked. For instance, I have some piezoelectric buzzers, and they always just show them, they tap it, and hey, look, there's a little spike. The way I thought it worked is you press it, there's a little spike, and then it's deformed to the new area, the new shape, and the voltage goes away. But as we saw here, when you have it set up like this, where I guess it's not just the one material, but you have these two materials like this, and you press it and you deform it, the voltage shows up, and it stays there. And in a minute, we'll show something else along those lines. So that's why it's like, oh my gosh. So it's not just a spike. It's you deform it with the piezoelectric material, and it's happily keeping the same voltage. So now, one thing you might say, and it's a reasonable question, is, well, maybe somehow it's still related to the differing electronegativities. So that's why I did this other copper plate. Now we're going to have the same material, just 2 plates of copper, and we'll do the same thing. So now we just have 2 plates of copper across a piece of balsa wood. And, you know, it's sitting there. I'm not prepared yet to say whether that's something or not. It might be, it might not. But let's do the same thing. So my hand's all insulated with the rubber and the plastic. Okay, so now it's just resting there, and I'm going to press on it. And it goes to there. Let it go. That's positive. Press on it. Press a little harder. It's actually going down now. And it's resting there. That's hysteresis, if I had to guess. Press on it. And there's a point of maximal voltage. So this is not dramatic. And you see, what I always thought was that that's all you could do with so it is piezoelectric. I mean, these are both, they're just 2 copper plates. There's no electrochemical thing that would be going on. And that's, you know, what they show. But what they don't show is, as I'm pressing on it, that's its resting voltage now. As I press on it, and I press on it a little harder, that's its resting voltage, and that's its unstressed resting voltage. Stressed resting voltage. Let me see if I can get it. Yeah. And you see there's like 2 components to it. There's the change in voltage component, which is more dramatic. That briefly spikes higher. But under stress, it doesn't rest. Here it is just sitting there. It doesn't rest there. One last time. It rests like there. And stays there. I know that, you know, you might not be impressed with 1 millivolt, but I am. So now I just want to do 2 more experiments and then wrap this up. Each experiment will have 2 parts. So, I mean, ideally it would be nice to have distilled water, but this is just filtered water. And then I have sodium hydroxide, which is a very strong base. So I'm going to put the sodium hydroxide into the water. What is it? Always add acid, so I imagine the same thing with a strong base. You don't just want the water hitting the base. Put that in there and get a strong basic solution for an electrolyte. I could use salt water, but I'm going to use this because I believe that strong basic solution keeps the copper from dissolving nearly as quickly, as well as the magnesium. And again, that's what they used. I think they used KOH, not NaOH. KOH on the moonshot with the zinc silver oxide batteries. All right, let me do this. So I'm not measuring the pH or anything. I just dumped a little bit of sodium hydroxide in there, teaspoon, maybe 2 teaspoons, and stirred it up. So now it says strong basic solution, and I'm going to dunk this in here. I'm going to leave it. I haven't done this yet. I'm going to leave it as the copper plates. Don't do that. You know, let me just let that sit in there. I mean, you could do it in the bath itself, but if I can just get the wood a little bit saturated, we'll also see a bit of a difference. So let me do that. So this is one I haven't done before yet, but then we just have it sitting there, and the wood's been soaked in sodium hydroxide. It's got a resting voltage now of 11 millivolts, 12. Now recall those are 2 plates of copper, so you want to argue that's electrochemical, then you'll have to teach me. Okay, so now I'm going to press on it. Again, I have no idea what's going to happen. Oh, look at that. It started off going positive, and then it went negative. Now it just goes negative, but it doesn't stay there very long. One more. Now it goes negative. I don't get that. I wonder if, oh boy, I wonder if I put in an acid, would it go positive? So I cleaned the plates off and cleaned them with a little apple cider vinegar. So now we're back to healthy stuff. So this is a bit acidic, and so I put a little apple cider vinegar and some water in there, and I'm going to soak this. And now we'll have an acidic electrolyte, and I want to see if it behaves the same. Okay, so now we've got the 2 plates hooked up to the meter with acetic acid soaked wood, and it's sitting at 0.92, which is about, what you'd expect, because this is a weak acidic solution as opposed to a strong basic solution, so it can't source ions as easily. All right, let me see if I can show this, because I find it fascinating. So I mean, it's sitting there around 9.26 now, and now I'm going to press on it. Sorry. But see, when I let go, it went below its original voltage. Now it'll take a while to try to climb back there. But the thing I'm trying to show here, if I can do it, it's just sitting there for the most part, 9.26. And originally it was like at 9.15 or something like that. So again, it'll take a while to go there, but press on it, just leaving pressed, pressing a little harder, even harder. Oh, I shorted it, sorry. So last thing is, let's do it under load. So again, I don't know exactly, I think it's 220 or something like that. But you see now, because it's a weak acidic solution, it's not really putting out much at all. What if I press on it? What's it gonna do? Ooh, baby. And now I'm just holding it there. Now it's still going down because it would be going down on its own. But that change, whew, Nelly, remains. That's better than I thought. Okay, boys and girls, that's it for this. Well, actually, I'm going to talk at you for a little while, and then we'll wrap it up. So the take-homes here are, one, I didn't know it's piezoelectric. It is piezoelectric. And I also didn't know that when piezoelectric materials are stressed, they continue to stay at a different voltage than their unstressed voltage. And if you release them, they overshoot and then go back to baseline. But if you press it, it'll stay at a different baseline voltage. And I was just lucky with the acid-base thing in terms of how that worked out. I didn't know that before I started. So then the next question is, well, what else is piezoelectric? And lots of things are. Quartz is, crystal radio. Quartz is, it's not only piezoelectric, it's ferroelectric. I'll get into that in a moment. But, I believe the piezoelectricity went back to the Rochelle salt, Rochelle salt. There, I think I mentioned this earlier on. You got your piezoelectricity, your pyroelectricity, and your ferroelectricity. Now, ferroelectricity is when you just have two plates, say both of copper, across a material, and it has a resting voltage. So people talk about the John Bedini crystal battery, the John Hutchinson crystal batteries, and I know John Hutchinson is given attribution to T. Townsend Brown. He talked about this, and what you can do with ferroelectricity. It actually goes back before him, and this is one of those weird things. I don't remember the name for it, but where like things get discovered simultaneously in different places, and it's like some monkeys in the Caribbean start peeling bananas, and then the monkeys in the Philippines start peeling bananas a week later. It was one of those things. So I think it was Maxwell, maybe one of those luminaries, who said, well, if there's a magnet, there should also be an electret where there's a permanent electric field. So around 1919 in Japan, I believe it was, someone first made an electric out of beeswax and carnauba wax by heating it, exposing it to an electric field while it was heated, and then letting it solidify. And once it was solidified, the electric field, just like magnetic domains, got locked in. Okay? At the same time, 1920, I believe, researcher, Czechoslovakian researcher in, I want to say like Michigan or somewhere, was looking at Rochelle salt, and he noticed when he applied a voltage to it, it didn't return to its original voltage. And they actually graphed, it was like a hysteresis curve. It tended to stay at the voltage that had been applied. And so this they deemed or termed ferroelectricity. And they're talking about, I would say, the same thing with electrets and ferroelectricity. They arrived at it through different means. And in the research with in Michigan, they were just hitting the Rochelle salt crystal with like 5,000 volts, and then it had a residual voltage, I don't know what, that just stayed there of like 50 or 100 volts. Maybe it was 1 or 2, I don't know. But I have started in on that paper, and it's very interesting, and I'm gonna plow through the rest of it. If people are interested, I'll do something just looking at the paper. So all ferroelectric materials are also piezoelectric and pyroelectric, but not all pyroelectric or piezoelectric materials are ferroelectric. So this didn't seem to have any residual voltage when it was sitting there, which would mean it's ferroelectric. But it is piezoelectric. I didn't know that about wood. So I really need to wrap this up because I'm just going on and on. But I thought that was worth showing. And, I know we're only looking at like 10 millivolts and things like that. But what can be seen is that a piezoelectric material under stress puts out voltage and current. And it keeps putting out voltage and current different than if it's not under stress. And that voltage and current, you need to like put a screw and washer or something like that, but it just keeps putting it out. There's got to be like some kind of word for that. I'm not sure what you'd want to call that. Okay, stay healthy, everyone. It's a difficult time to do that. Stay healthy, and thanks for coming along for the ride.